Let us now turn to the study of the early universe. First, let me review a few of the key ideas. Obviously, as already Lemaitre realized, as you turn clock backwards and go towards smaller universe, it was hotter and denser. In a fairly predictable way, since we know how matter behaves under high densities and temperatures, although, of course, some new interesting physics can happen, such as inflation. At any given time, particles in the universe have certain temperature, meaning certain energy, and that means that particles of different rest mass energies would dominate at different times. Essentially, universe acts as the ultimate accelerator, reaching energies of particles that will probably never be generated in a lab, and thus providing a very interesting new window into particle physics itself. So as we go deeper in the past, the energies increase, and we get into regimes where different interactions and different particles become more dominant than others. However, the price of that is that the deeper we go, the higher the energy, the less we actually know. We currently probe physics out to the energies of the order of 100 tera electron volts of rest mass, and we do have fairly reliable theories what goes on up to there or thereabouts, but beyond that things get to be increasingly more speculative. And in any case, at some point this has to break down. Currently, the best guess is that it breaks down around the Planck time, which is more or less a guess. We will discuss Planck units later, but at any rate, 10 to the minus 43 seconds is certainly the boundary of what we can even guess. Here is just a schematic outline what the history of the universe might look like. There is a very early period of inflationary expansion, which is by now, I think, fairly well established, but is by no means proven. And then we go through the early universe, a hot soup of quarks and other particles, until the atoms form, they recombine, microwave backgrounds released, and that's where the astronomy as we know it really begins. So let's go quickly through thermal history of the universe. What are the key moments? At some point, quantum gravity has to be important and dominate the physics of the universe. We do not know when that is. We do not have a quantum theory of gravity. And Planck time, 10 to the minus 43 seconds, is about as good guess as any. The inflation, if it happened when the universe was around 10 to the minus 33 seconds old. And shortly thereafter, we believe there was a grand unification, or rather splitting of the electroweak interaction from the strong interaction. They split from gravity sometime earlier, probably prior to the inflation. When the universe was around a microsecond old, baryogenesis happens. Quarks create things like protons and neutrons, particles that we know about. Between about 1 millisecond after the Big Bang, in about 3 minutes, is the time of the cosmic nucleosynthesis, where the light elements, stable light isotopes like deuterium, helium-3, helium-4, lithium, a little bit of beryllium, maybe even some boron, were formed and frozen. At that time, the universe is still very much dominated by radiation. That changes around the time of around 100,000 years age, after which matter becomes the dominant component of the dynamics of the universe, and first structures begin to form. The seeds of the first structures begin from the dark matter itself. And when the universe was 380,000 years old, and we know this number fairly well thanks to the precision cosmology measurements from cosmic microwave background, the gas becomes neutral. Electrons and protons recombine, become atoms of hydrogen and helium, and the universe continues to expand. At that time, there are no more sources of light. There are no stars and no galaxies. These begin to, we think that they begin to form when the universe is a few 100 million years old. At that point, they can reionize the neutral gas of the universe, and that is pretty much completed by about age of 1 gigayear. And that's where right now the frontier of our observational cosmology is. Physicists love to plot time history of the universe on the log axis because that gives a lot more space at very short times in which they're interested. And all of the known astronomy happens just over there in the corner at the end. Well, here is one from Mike Turner, and it's a handy little chart because it shows you the temperature, meaning the energy of the particles, the density, as well as the time when it happened, with few of the key moments noted, just as I outlined a moment ago. In a tabular format, here is a quick outline, again, of what are the key times and particles that dominate or processes that dominate at that time. Not to be too boring, but here is another one. All of them contain more or less the same information. I'm offering all of them to you because you may find one or the other more useful or more clear than the others. Well, what is the empirical evidence for all this? The first and foremost is the cosmic microwave background, our direct probe of the early hot dense universe. So that reaches to the times when the universe is a few 100,000 years old, or reaches a little in excess of 1,000, and it's certainly based on a very well understood atomic physics. Next comes the cosmic nucleosynthesis, and that's based on well understood nuclear physics. The results of that are abundances of light elements that we can test observationally today, so both experiment and theory seem to be fairly reliable, pushing in towards the Big Bang all the way down to maybe 1 millisecond. Beyond that, things get to be increasingly more speculative. We think that the asymmetry between matter and antimatter in the universe was set around the time when the universe was about a microsecond old. This is based on a reasonably reliable physics of the standard model of particle physics. Nevertheless, it's not necessarily firmly established, but you can think of the actual observation that there is a lot more matter than antimatter in the universe as an evidence of what may have happened when the universe was a microsecond old. Then we reached the inflationary era, when the universe was 10 to the minus 32 seconds old. Inflation makes some very testable predictions, and so far seems to be doing fairly well. A lot of people believe that something like inflation must have happened, which would be really remarkable, giving us an insight into the physics of the universe when it was only 10 to the minus 32 seconds old. But the upshot is that cosmological observations of the largest things we can think of, can constrain particle physics, microphysics at the smallest scales we can also think of. Well, let's first talk about the cosmic microwave background. In some sense, its existence is trivial prediction of Big Bang theory. If the universe was expanding from hot and dense state, then there has to be a thermal radiation relic from it. Initially, universe is all plasma, everything is completely ionized, there are no atoms, and when it gets cold enough for atoms to form, this is where this thermal radiation gets released. So Alpher and Hermann, Gamow and others made that prediction in 1940s and actually estimated that the temperature of the cosmic microwave background will be around 5 degrees Kelvin. It was only in 1960s that cosmologists began to try to detect this in a serious fashion, and there were upper limits until the actual discovery by Penzias and Wilson. However, there was an even earlier, not quite discovery, as early as in 1941, and here is how. There are molecules in space, and there are clouds such as cyanogen. Cyanogen happens to have some energy transitions that are highly sensitive to temperature and probe the regime around few Kelvin. So Walter Adams obtained observations, and Mackellar had a theory inferring from these observations of these subtle little lines of cyanogen that gas was in a thermal bath of a couple degrees Kelvin. They didn't make anything out of it at the time. You could think of other ways to heat up molecular clouds, like with starlight, and that stayed forgotten. Certainly Gamow didn't know about it until Fred Hoyle, of all people, the person who was against the Big Bang, dug up this evidence and pointed it out, that this could be in fact a consequence of this thermal background from the early universe. But then again, it was a little too indirect and subtle for most people to believe. It took really direct discovery by Penzias and Wilson to make a solid case for the existence of cosmic microwave background. Clearly, this was a real milestone of cosmology. So as we know, the universe is filled with a thermal radiation. Temperature is 2.7 degrees Kelvin today, and it's essentially a perfect black body. We have looked for deviations from the black body spectrum, and none were found. You could imagine such things happening if some energetic processes in the early universe dumped extra energy into it and changed things away from the equilibrium thermal black body radiation, but evidently this did not happen. So the good news is that physics is well understood. We know exactly how this went. The bad news is there were no surprises. There was no new physics to be found. The key discoveries there came from the COBE satellite, Cosmic Background Explorer. COBE was launched to probe cosmic microwave background in ways that would not be reachable from the ground, at least not at the time. And here are pictures of cosmic microwave sky. This is the top one, has the contrast knob turned up to 1000, and you can see the dipole radiation, which was already known due to the motion of the Milky Way relative to the cosmic microwave background. Subtracting that and turning the contrast knob to 100,000, you see motley sky and a big plane of galaxy with thermal emission from dust and synchrotron electrons and whatnot. And subtracting that galactic emission leaves just motley sky of fluctuations that were primordial in nature. Cosmologists long looked for those, but this was the first time they were actually really seen. And it was one of the reasons why John Matter and George Smoot got Nobel Prize for some of these discoveries. So let's estimate when exactly the recombination of primordial plasma into the atoms happens. Hydrogen becomes ionized if it absorbs photons with energies of 13.6 electron volts or more. And this is 3 times Boltzmann constant times the equivalent temperature of the gas. So that immediately implies temperature of around 50,000 degree Kelvin. However, turns out, since there are many more photons than there are protons or electrons, about by a factor of 1 billion, even a tail of high energy photons from a cooler gas or cooler temperature would suffice. And we can estimate that using Boltzmann equation for equilibrium shown here. And it happens that given this overabundance of photons over protons and electrons, the temperature could be as low as 2500 degrees, and already one can get recombination. Since the observed temperature of the microwave background is now about 2.7 degrees, this immediately tells you that this happened around redshift of 1100. Well, obviously it doesn't happen all at once. There is a transition period, as shown here. What is plotted here is the fraction of ionized hydrogen in the universe, which begins at unity. It's all completely ionized. Then slowly the gas recombines, the electrons are bound into the atoms, and the process ends by about redshift of 1100. So when we look at the cosmic microwave background, what we're looking at is a photosphere of the hot ionized universe, inside out. When we look at the star, we see a photosphere of ionized gas from the outside in. So this is the inverted version thereof. You may recall when we talked about models that dominated by matter versus radiation, that because the energy density of photons changes in a steeper way with expansion than does of the matter, the two components must dominate at different times. The energy density of the radiation decreases as the 4th power of the expansion factor, whereas for the matter it's only 3rd power, simply dilution in volume. And so given today's densities of matter and microwave background radiation, which is well determined through a Stefan Boltzmann formula, we can find at what point did these two cross. And the answer is around redshift of 5000. So this was before the recombination, but well after cosmic nucleosynthesis was complete. Next, we will talk about cosmic nucleosynthesis.